lesser quality. Okay, so for those of you that might not have been around, my name is Evan Wilson. I'll be substituting for Dr. Horvath for the next 2 weeks' time, up through the 20th, up through your second exam. If you need to get in contact with me for any reason, my email is right here. It is not Mosan71, it is Mosan, M-O-W-S-A-M 71. So make sure you have that right. Don't email or don't message me over Sakai. I'm on the Sakai website. I hardly ever check it, to be honest. So if you need to get a hold of me, that's the best way. I check my email at least a few times a day. So I'll be able to get back to you pretty quickly. I also check it sometimes. Now, I want to take a quick poll here. How many of you guys go to Dr. Horvath's office hours? Okay, a couple of you guys do. Now, in substituting for Dr. Horvath, I would also like to be able to cater to you guys that normally go and talk to him. Would you like me to have office hours at a certain time during the week or immediately after class or something like that? Or would you like to do something like that by appointment? Should you need the help, I'll be able to free myself up over the next 24 hours or so. What's your personal preference? For me, I've got a pretty free schedule besides what I do here. It's really up to you guys. No, don't everybody talk at once. I can't hear everyone. Okay, so what I'll do is I might go ahead and send a message out to you guys on Sakai. You can get back to me, and we'll talk about something like that sort of over the internet as we go along through here. If you need some help, I want to make myself available to you beyond what Sue and Lynn do in their office hours. So, I believe we left off yesterday right about question 1863. Everybody was packing up. Dr. Horvath was shouting at you guys, trying to get everybody to hear his last thing to say. But I think we ended right at about question 1863. We had the charge balance equation written out here. Sort of written as John Madden would write it, as messily as possible. But you have sodium ion and hydronium ion are your two positive ions in this solution of sodium bicarb. And then for your negative ions, you have, of course, bicarb ion itself, 2 times the doubly negative carbonate ion, and hydroxide ion. Now, we know that this is set to 0.10, which is also the concentration of the sodium bicarb. Why can we say that? All right, well, we know that this is amphoteric. It acts as both an acid and a base. Its concentration is not going to equal 0.10. Similarly, here, these concentrations can't be set to 0.1. So we can't get our charge sum from the negative ions. Now, yesterday in class we established that sodium ion was in fact at a concentration of 0.10, which means we can ignore hydronium ion because, as again we said yesterday, hydronium ion doesn't really count if you're in a basic solution or a measurably basic solution where you don't have to include things like Kw. So, we know from sodium ion the summation of these 3 negative ions has to be 0.10. We're going to be able to take advantage of that as we go on through and we solve for the concentrations of all 3 of these things, as well as the concentration of the neutral H2CO3, hydrated CO2. So, does anyone have a question on how we got this charge sum? This is the kind of question you guys will likely be faced with as you go on towards exam 2. It's a good way to save some space. What's up?
Since there's 2 CO3, 2 minuses, why don't you double the charge balance? Because that's what you did for the other one.
Why don't I double the charge balance? Because I don't know this concentration. Now, if this were the only one here, then we would know its concentration well. But since that's not the salt, if it were sodium carbonate, then this would be 0.20. But since I've only got some bicarb floating around, the only way I can actually get a hold numerically of charge balance is through sodium ion. So if this were the only negative ion present, and it didn't act as a Bronson-Lowry base, then I would be able to assure that that is 0.2. But since there are other things going on, since I do have some acid-base activity with the bicarb, I have both carbonate and hydroxide. I also have bicarb floating around. So I really can't assert anything numerically from what I have over on the left-hand side here. So the only time you'd be able to really double that charge balance is if you're sure that something is going to be at 0.2. So you just know the concentration of sodium ion here, so that's the only thing that's going to give it to you directly. Additionally, if you're faced with that kind of thing, if you have sort of a logical problem with this, if you're solving this by yourself, you think, okay, when I take 10th molar sodium bicarb and dump it into solution, it all dissociates. If I set sodium ion to 0.20, I know I've done something wrong because the most amount of sodium ion that I can have in this thing is 0.10. That's another way to think it through if you're ever not sure, like, should I double this charge balance because I see that factor of 2 there? You can just say no because you can look at your original equation. This isn't a semi-soluble salt. We'll talk about those later today. So that's going to dissociate completely, gives you 0.10. So are there any other questions about charge balance before we move on to actually going ahead and solving this equation? Cool. All right, now, what I'm going to do is I'm going to go through, I'm sort of going to go through the really important points that Dr. Horvath brings up over pages 18, 49, 50, and 51. He goes through all of this. I've done my best to stick to his nomenclature system, so you can both follow along the book and take whatever notes you might find important. So, when you have a problem like this, you have 3 unknowns. We also have 3 equations. We have Ka and Kb for bicarb ion. And we've also established charge balance, for which we have 0.10. So we have an equality there as well. Now, the way we're going to do this is, rather than sort of use all these symbols, which can become a little bit cumbersome, we're going to set them equal to just algebraic variables, x, y, and z. As we go through this, it's very important that you always go back to your key and know what's what, x, hydronium ion concentration. I see that in Ka. So why the hell do I have Kw over x here? Oh wait, this is Kb, so Kw over x, that's actually hydroxide concentration. Things like that. So don't lose the chemistry, even though we're dropping the symbols and we're going to x, y, and z. We're just saving some space here. So, I'll write out my other equations, Ka and Kb, in terms of x, y, and z. Here we have x equal to hydronium ion, y equal to carbonate ion, and z equal to H2CO3. Now, I'll be able to solve for all of these, eventually. So, I just have those written here. Now the first step that I'm going to do is I'm going to take my most simple equation, charge balance. I don't have to worry about sodium ion. It's not going to do anything in solution. It just floats around there, but it gave us a numerical handle on charge balance. Thank you, sodium ion. We don't need you anymore. So, use charge balance. I'll go ahead and I'll solve for the concentration of carbonate ion. In doing so, I get Y, concentration carbonate ion, equals Z minus concentration hydroxide ion, just Kw over X. Nothing that you guys haven't seen before, but it's in symbols, so it might seem a little bit more cumbersome, I guess. So, that's just in solving, simple subtraction, a little bit of algebra there. Now, the next thing that we do is we go ahead and take this Y. Now that I've defined Y in terms of my other 2 variables, just a simple system of equations, you guys probably did this in high school, I can go ahead and take this and substitute for Y in Ka and Kb, which is what I've done up here. This is the same thing that Horvath has written down. He did it in a couple more concerted steps. I just wrote down the simplified versions that he has there. Now, again, I want to make sure that all this stuff makes sense. You can go through and you can check it yourself. We're not going to do it here because we know that we've done this right. But Now, I'm left with an important thing. 2 equations, 2 unknowns. This is generally pretty easy to do, but this is probably a little bit different than the stuff you guys have seen in high school. If I went through and I solved this algebraically rigorously, it would take me a little while. And I don't like spending a lot of time on things. So how are we going to solve this? We're not going to use rigorous algebra to get this all in terms of one variable. What we're going to do, we're going to do the good old-fashioned guess and check method. But we're going to be smart about it. What we're going to do, similar to what you guys have done in the past, with percent ionization, where you get a maximum percent ionization and a minimum percent ionization, and you consider, okay, I'll take the halfway point between those two, try that, and then continue trying until you get a suitable answer. What we'll do is we'll take our maximum hydronium ion concentration and our minimum hydronium ion concentration, and we'll take the halfway point between those two, and then we'll go ahead, we'll plug that in, solve here, check it here, and see if it's right. If it's not right, we've used the halfway point, so that way we've eliminated half of our possible concentrations of hydronium ion, and we can go on, continue guessing and checking. Generally, since we're only out to 2 significant figures, this should only go through once or twice. A lot of the time, halfway point gets you pretty close, so you only need to go ahead, divide that by 2 again, gets you right there. But, if we don't know how to get hydronium ion maximum and hydronium ion minimum, we have a very large pH range to cover. So, we'll do the easy one first. What's the maximum hydronium ion concentration in this solution? 0.1 molar sodium bicarbonate.
1.0 times 10 to the minus 7.
1.0 times 10 to the minus 7. Easy. So, we've already proven to ourselves by taking a look at the Ka and Kb values of bicarb ion, this solution is basic. Mildly so, but basic. So, I'm going to set my maximum hydronium ion concentration to the breakpoint of neutral, 1.0 times 10 to the minus 7. Does anybody have any questions on how we got there? Just because it's a basic solution, we're picking a neutral hydronium ion concentration. So that way we've eliminated pHs from 0 to 7, because no, it's not from 0 to 7. Okay, so a little bit less easy. I say less easy because it's still easy. How do we get the minimum hydronium ion concentration? Now, you can also think of that as the maximum hydroxide ion concentration as a hint.
So you get it from using the Kb and setting it to x squared over mi minus x.
Yes. Now, Dr. Horvath does this for you guys here. He uses A. Because we've already used X, doesn't matter, it's just a variable that to us represents hydroxide ion, A squared. So, even says that right there. A equals hydrated CO2, also equals hydroxide ion. This is about midway on page 1850. Now, if you go ahead through and you solve this, you get a number. Number for A, 4.9 times 10 to the minus 5 molar. Now, is that my minimum hydronium ion concentration? No, right? This is maximum hydroxide ion. So I need to convert this back to hydronium ion for Kw to give me a value of hydronium ion. So, go through that math. H3O min, Horvath has it written for you right there. You need to write Kw over whatever that is there. 2.0 times 10 to the minus 10. So, rather than having to deal with 14 powers of 10 to guess and check for hydronium ion concentration, we've narrowed it down to between 1 times 10 to the minus 7 and 2 times 10 to the minus 10. While those numbers aren't necessarily close to one another, they're much better than we would have done before if we were sort of feeling around in the dark. This is a good thing to know. One of your maximum values, one of your minimum values is going to be easy. The other one, also going to be easy when you're looking at a problem like this, but you got to know to go through either Ka or Kb depending on the problem. So, does anyone have any questions before we did here? H3O max, H3O min. Okay. So how many of you guys studied logs in high school? Pre-calc, calculus, get around it. How many of you guys remember anything about them? Yeah, okay. That's about part, of course. Don't worry about it. So, what we want is a halfway point. So I need the concentration halfway between 1.0 times 10 to the minus 7 and 2.0 times 10 to the minus 10. Now, if I want to find an arithmetic mean, normally what I do is I just tally these two things up and I divide by 2. Easy, right? It's not quite that simple, but it is still pretty simple. Now, concentrations. You see powers of 10. These relate to one another exponentially, so we can't just add them together. That doesn't work, which is why we use logs. Logarithms are a tool. What they allow us to do is they allow us to take things down. So rather than use these, which are exponential, I'm going to go ahead and take the negative log of these to make them additive. So I'm going to calculate what these two pH values are, and then I'll do a simple arithmetic mean. So, pH value, H3O max. This is a tough one. H7.0. This one's a little bit tougher. PH 9.7. Now, since I've applied my logarithm, I can add these two together, 16.7, and I can divide by 2 to get my pH, which is halfway between these two concentrations. So 16.7 divided by 2, halfway pH is 8.35. This is going to be the pH that corresponds to the concentration of hydronium ion that I'm going to try first when I'm applying a guess and check in here to solve for the one remaining variable, Z, which is the concentration, H2CO3, hydrated CO2. So, does anyone have any questions there? This is a really popular Horvath question. If you guys have looked at past multiple choice exams, there are plenty of questions like these, and there are plenty of questions like these that unfortunately have diamonds around them because people miss them all the time. Very simple. First you start with concentration. Go to pH. pHs are additive. Concentrations are not. Multiply, or excuse me, add them up. Divide by 2. That gives you halfway pH. And I can go back from halfway pH to concentration to get halfway concentration. I don't know if you guys will see this on your exam. I don't know if it's a popular long answer question, but it's probably something that you'll need to at least apply if it's not explicitly asked of you. Make sure that you guys keep this in mind. It's a simple procedure, but a lot of people miss the step. First convert from concentration to pH, or arithmetic mean, then you get halfway pH. You can go from halfway pH to halfway concentration. Now that I've beat that horse to death, any other questions? Okay, so halfway pH, 8.35. Halfway concentration, 4.5 times 10 to the minus 9. Okay, so am I good to go ahead and erase some of this stuff here related to the halfway pH? Okay. Now, since I have two equations and two variables here, I could use either one to first plug in for hydronium ion. But what I'm going to want to do is I'm going to want to use the one that gives me a more direct handle. I'll just use Ka. So that's Ka. Ka is just a number. So I'll erase that. Ka for bicarb, 4.8 times 10 to the minus 11. So what you can do here, this is 7th grade math here. All you have to do, cross multiply, carry this through, make sure you distribute appropriately. I'm not going to go ahead and go through this. Try this by yourselves. Don't look at Horvath's book. Start right there. Make sure you can get to the correct answer. Cross multiply, distribute. You'll find Horvath ignores a couple terms here. When you end up multiplying 4.8 times 10 to the minus 11 times 2.2 times 10 to the minus 6, you get nothing. Something on the order of 10 to the minus 17. You can ignore something like that, so long as it's not a factor of your variable z. So, when you go through that, if you see an extremely tiny number, feel free to ignore it, so long as it is its own term and it's not multiplied by z. Now, what that will do, that'll give you a number for z. Z equals 1.0 times 10 to the minus 3. So, a couple steps later. Always remember that you're dealing with concentrations here. Horvath sort of drops that off, probably to save some space, make it a little bit easier for your eyes. I'm trying to include it whenever I can because, again, if you just start looking at numbers and letters, you lose the feeling of what's really happening, and that's what's most important here. So, thousandths molar, Z. So what does that mean? Go back to my table. Z, concentration H2CO3. Now, I've got an answer. I don't know if it's right or not. Basically, all I've done is I've taken Z and I've fit it to a number that I made up for X. I made it up wisely, but I still made it up all the same. To double check yourself, what you'll do take this value for Z, plug it into Kb. Use the same value for X that you used, hydronium ion concentration from our key. Plug it in here. So that way, you'll be able to solve for this number by just doing math. And then you'll compare what you get here to the numerical value for Kb. If the two are the same, or very close to the same, say within, I don't know, 5% or so, you're in really good shape. You don't have to go through again. And in this case, the numbers come out to be correct. Once again, all this is algebra. Plug numbers in here, you'll get a value for Kb equal to 2.2 times 10 to the minus 8. And the actual Kb is 2.4 times 10 to the minus 8. Very, very close. According to Horvath, close enough. You come that close on a bonus quiz, you come that close on an exam, we'll take a look at your math. If you've done it right, that's full credit, if you're interested in points. So, that's the way you go through and you solve one of these. You have a system of equations, take it very slowly, make sure you always understand what your variables mean. Because if you start to miss that, you replace one variable with another, unquestionably, you'll get the wrong answer. So, do things very slowly. Once you break things down, do a smaller system of equations. 2 equations, 2 variables. What you're going to do, rather than you can solve it rigorously out of grade. That's totally fine. I find, and Horvath finds, the easier way to do it, find H3O max, find H3O min, find your halfway pH, find your halfway hydronium ion concentration. Plug that in, solve for your last variable, double check yourself with the second equation. If you're close, you're done. If you're not very close, have a think. Does this need to be bigger or smaller? Maybe go to the halfway point between this and the maximum, or this and the minimum. It needs to be larger or smaller respectively. Try that again. And then the second, maybe the third time. I don't think for a Horvath question I've ever had to go beyond 2 of those. Double check yourself again. You got the answer. Now, does anyone have any questions on this? It's kind of a long process. There's a lot of math involved, but that's sort of the nature of the beast.
So, how exactly, the question originally was asking about why the charge sum value. What about I'm not exactly the question.
Oh, okay. Yeah, so question 1863 stands by itself. And then solving the problem for Horvath means solving for all the concentrations of things that you don't know. So that's, well, it's directly related to charge sum in that we need this charge sum value to actually solve. It's not saying like, we're not going through all this just to say that the charge sum is 0.10.
Okay.
Yeah, no, that's a really long walk for a really small drink of water. No. So what we're doing in this case, we want to solve for hydronium hydroxide ion concentration. We only need one to get the other. And we want to solve for bicarb, carbonate, and H2CO3. And I know that once I have 2 of these, I can solve for the third one because I know that all of my carbonate-containing species, bicarb, carbonate, hydrated CO2, have to add up to this number. So that's the way I get to the last one. Any other questions on this process? I suggest you take a second look at it. Generally, it's easier when you have the answer floating in front of your face. Take another look at the same question later on. Try to run through it yourself. Spend 10 minutes on it. And if you run into a problem, if you say, well, I can't get through 1 or 2 different steps, send me an email about it. We'll talk about it, or I'll be able to email you back what you might be doing wrong and how to avoid that problem. Okay. So, that brings us through 1851. Dr. Horvath makes an interesting conclusion at the end of that. We find that our concentration of H2CO3 equals the concentration of carbonate ion, CO3 2 minus. And that's because of this unique pH, 8.35. If you go through and you solve everything, you'll see that bicarb ion at pH 8.35 is just as good of an acid as it is a base. That's all that it's saying to us. So for any amphoteric species, there is going to be a magic pH at which this species acts equally as well, equally as good of an acid as it is a base. For water, that pH is 7. Yeah.
So is that what we're finding, the pH at which it acts as both an acid and a base?
That's not what we're finding. We sort of found it by accident here. Just because the pH of 0.1 molar bicarb ion happens to be that magic pH. If we had a different concentration of our original salt, we would be at a different pH, and that wouldn't hold true. But this is just sort of an interesting case. This is a unique one. That's not going to be the case every single time. So that's not a way to double check yourself, but it's sort of something that Horvath sort of looked at and cocked his head aside and said, I should make a note of that. So that's interesting, but beyond that, it's not really of use to us, but it's cool to know that for every amphoteric species, there is a magic pH at which is just as good of a base as it is an acid. And again, that pH is 7 for water. So we already sort of knew that. Okay, so moving forward, we got 2 last questions. The end of chapter 18 before we jump into semi-soluble salts. Question 1864. Looking at a different species. We have an acidic cation, ammonium ion. So we want to know pH 0.10 molar, ammonium bicarb. Versus the pH of 0.10 molar, sodium bicarb. Now, we're not going to go through this calculation. It is more difficult than the one we've just done because we have an acidic cation. Now, all we're asking for is qualitatively, is the pH of ammonium bicarb going to be less, more acidic, or greater than, more basic than sodium bicarb? What do you think?
I think it'll be a little more acidic, but it'll still be allowed for a weak base.
A little more acidic, but it'll still be a weak base. Exactly. Now, let's see here. Will it be mildly acidic or mildly basic? You're stealing my thunder, man. All right. So, the solution will also be weakly basic. Why?
Because the Kb of HCO3 is greater than the Ka of it, and that Kb is greater than the Ka of H4, and you know, ionize more, or better.
Which is also greater than the Ka of bicarb. Exactly. weakly basic solution, slightly more acidic than the original one. So if I were to take steps to start to try and solve this one, I'm going to take advantage of what I already know. Question 1865. In calculation, the hydronium ion concentration for 0.10 molar ammonium bicarb by establishing values for hydronium ion, that is, hydronium ion max and hydronium ion minimum. What boundary values would be obtained in light of the above pH calculation for sodium bicarb? So, what's going to be hydronium ion maximum? This is another easy one. Same thing that we had before. I know it's weakly basic. Ka and Kb told me so. 1.0 times 10 to the minus 7. I'll use my breakpoint for acidity. Well, for an acidic system. Now, we can use our logic for hydronium ion min. What do you think we should use? The same minimum value that we used before? I'd probably give that answer half credit. Two point zero times 10 to the minus 10? Yeah.
Since you already know that that's, it's within the boundaries of NaHCO3, so you would just use that H3O value. The true one, the 4.5 times 10 to the minus 7.
This is the one I'd use. Save some time. You could use this one. That'd be okay. But your halfway pH would probably be skewed a little bit. You might have to go through another iteration of calculation. And nobody likes just crunching numbers. So the best idea you can get is to use this, which is the H3O true for .10 molar sodium bicarb. So, you can use information that you solved for in the past to help you solve future problems. Now, how are those two questions? 64 and 65, just basically taking some knowledge that we've already got, applying it to another question you might want to solve in the future. Yeah, you might actually have, no, he already gave you the answer in the challenge problem section. I'd imagine on a bonus quiz he'll give you a question like this where you have acidic cation and basic anion. They're tough questions, but you'll learn how to solve them as we go on. So, any questions on chapter 18 as a whole? Okay. So, challenge problems are for you guys. Challenge problem 18-2. That was on one of last spring 2013's bonus quizzes. That's a great question. It's not really rather simple. Horvath realized that himself last semester, so that's why it was on the bonus quiz last semester. So, 18.2 is a good one to look at. You can look at how it's solved as well. 18.4 is another one, good one to look at. Let's solve those two if you're interested in doing challenge problems. 18.4 is, that's a good question, I like that one. All right. Question 18.4, know your moles. All right. Now, there are no further questions on chapter 18. We'll go ahead and get into chapter 19. Semi-soluble salt equilibrium. Now, there are a couple things that you might know about this topic already. Sodium chloride. Is that soluble? Not a trick question. Yep. Calcium carbonate. Chalk. Is that soluble? Did somebody just say semi? Good answer. Yeah. So it goes into water, but not very well. That's what we talk about when we talk about semi-soluble salts. This is why gymnasts, they'll use a bag of chalk because they don't want their hands to stick to things. Now, while some calcium carbonate does go into water, most of it doesn't. So, even if I have sweaty hands, they're not going to stick to anything. So it makes using the uneven bars or the rings or whatever the hell else easier without sticking and falling off. So, you have on your information sheet a table that gives you KSP values. And you probably looked at this and say, well, gosh, I hope we don't get there this semester. This seems different and will therefore be difficult. While it is different, it is extremely similar to what we've done before. Now, that little introduction, we'll read through some of the things that Dr. Horvath has to say. So, semi-soluble salts, ionic compounds, sodium chloride, calcium carbonate, hundreds of thousands of others, I'm sure. Moderately to sparingly soluble in water. Now, that's a very general term. I think he says here, for a semi-soluble salt, the maximum concentration should be around 200th molar, 0.02 molar. Is going to be a saturated solution of this salt. So not a lot's in. The minimum value, you see anywhere from 1,000th molar to 10,000th molar, depending on what kind of chemistry you do. If you're an analytical chemist and you have a very sensitive instrument, you can throw a whole lot of zeros before that, and your limited detection is going to be very low, depending on the sort of instrumentation you're using. We won't talk about that, though. That's something for analytical chemistry. So, semi-soluble salts, we'll use the first one he says there, between 1,000th molar and 200th molar. So that's a saturated solution of this salt. Now, the last sentence is very important. Of course, in a saturated solution of a semi-soluble salt, equilibrium exists between the constituent ions and the solid form of the salt itself. Now, that's going to allow us to get a handle on the concentrations of these ions in solution. And the more that we know about a given solution, the more we can do with it. This is an extremely important thing, because we're given another K value. KSP. Again, you guys have seen this on your information sheet. It looked different. There's nothing to be intimidated by. This is often called the solubility product. Which is probably why it's subtitled SP. Now, don't confuse KSP with solubility. Horvath likes to use a little cursive S, I think, while he's writing up on the board. You'll see it as probably an italicized S in the text. We haven't quite got it. So, little s, solubility. Let me do better than that. Little s, molar solubility. Now, as you could probably imagine by what I just called it, it is measured in moles. This is what allows us to get a handle on concentrations of constituent ions in a solution. So, we have a KSP value, we've got S value, and S value can be likened to what you called X when you were doing Bronsted-Lowry acid-base chemistry. It's just a variable, talking about concentrations of your constituent ions. So, our first example, MX, bottom of page 19.1. MX is a solid. And I've tried to dissolve some of it in water, but it doesn't all go in. So I've got an equilibrium between M plus, let's assume they're both monocationic and monoanionic, and X minus. Let's pay attention to phase here when we write our equilibrium expression. Solid. Both of these are going to be aqueous ions. So, if I wanted to write a K for this reaction, what's it going to look like? I'll give you the first one.
It's just going to be MX.
Yes.
And that's
Concentration of
Yeah,
N times the concentration of X. Well, N plus. Times the concentration of
you're good, you're good.
I'm used to word that.
What? All right, no. All right. So we call this K KSP. No different than any other K, it's just got a special name. So, easy, fantastic. Now, of course, things can get a little bit more complex. So say I've got something like the bottom, A2, B3, subscript numbers. A2, B3. Again, I try to dissolve this into water, it doesn't go all the way in. So I've got an equilibrium between aqueous A excuse me, I don't need concentration brackets here. I don't know what the hell I'm thinking. That's my one deliberate mistake of the day. Nobody caught it, I'm disappointed. And again, A2B3, solid. Remember, it doesn't belong in an equilibrium expression. That's a common problem that we see when people work exams, when people work bonus quizzes, whatever. People oftentimes try to include this in an equilibrium expression, and it leads them nowhere because they say, well, I've got, I don't have a number for this. You don't need one. So it doesn't belong anywhere in an EQ expression. All right. Now, I'm going to symbolically represent this KSP using A and B.
Is it, I don't know, I'm just thinking about for like the 3B 2 plus or is it 2 minus, just because I know it looks like minus. I just don't know.
Yep. Yeah.
3A 3 plus squared, multiplied by B 2 minus Q.
Exactly. So, yeah.
So how do you know when you use K as opposed to KSP? Because
the difference between KSP and K? Or, there's none. This is just a special name for it. So if you see semi-soluble salt, you're going to want to look at your solubility product table for KSP values. Dr. Horvath could just as well call everything K, but then that would get super duper confusing super duper quickly. Once we get onto complex Ks, which aren't that complex, you're going to want to differentiate KSP, KW, KA, KB, etc. So, we just give it a special name and real difference there. Okay, so, from here, we move on to another question. Now, this is just another K. We can do Q's, doesn't much matter. So, let's see here. What can happen in a solution of a semi-soluble salt if the molar concentration product of the constituent ions, Q, exceeds KSP? That is, what can happen if Q is greater than K, SP? Now, if I have too many ions in my solution, I want to have a reaction that leads me towards a new equilibrium. So this reaction is going to proceed in which direction if Q is greater than K? Perfect. So this is going to be my Q greater than K. So, this reaction is going to proceed to the left. What do you call that when that happens? Precipitation. Now, Horvath words this wisely. He says what can happen. Now, if I take a solution, a hot solution of water, and I dissolve a bunch of sugar in it, and then I cool it down slowly, something called supersaturation can occur. We're not going to touch that. But it's important to know, in our case, whenever you see something like this, expect precipitation. We're not going to deal with supersaturation, which is how soda is made, by the way, not the diet stuff, the better stuff. So, precipitation can occur. Now, it's an important thing to know. All this is an equilibrium. If it's not an equilibrium, a reaction will occur to establish equilibrium, re-establish equilibrium. Q greater than K. And if I just take some A2B3, and I dump it into water, and I don't have any A in water, and I don't have any B in water, the opposite is going to happen, because Q is, of course, going to be less than K.
What would you do for the system to make it less than
So if I just take some water, if I take a liter of water, and I dump some solid in here, some solid A2B3 into it, Q is, of course, going to be less than K, because all I have is water. I have no A3 plus, and I have no B2 minus. So Q is essentially going to be 0. Q is going to be 0. So that reaction will occur, pushing things to the right until equilibrium is established. So any questions on just sort of general things? Yeah.
Is there a particular name for Q less than K, like dissociation, or, because we did,
Dissociation.
yeah,
Is the exact word.
Okay.
So dissociation will occur if Q is less than K.
Okay.
You don't really need to worry about nomenclature, but that's the common term for it. Ionic solution, or ionic solid will dissociate with water to some extent. Okay. So 19.2, A through E, we have an overview of the topics that we'll be going over regarding KSP. There's quite a bit to it, but we'll start with the simple stuff. A, calculation of salt solubility where the constituent ions of the salt do not have appreciable Bronsted-Lowry acid-base properties in water solution. For any such case, S can be calculated solely from KSP. So, we're going to go over some simple examples. This is basically just solving for concentrations using an equilibrium constant given to you. You guys know how to do this stuff. It actually starts out a little bit easier than acid-base chemistry. So, we'll take a look. 19.2, about 2/3 of the way down. Calculate S for silver chloride in water at 25 degrees, given a KSP value. Can I erase this stuff? just have this written as silver plus. Silver will attract 2 water ions in solution. So that's actually silver, parentheses, O2 sub 2, close parentheses 2. But I'm just writing it as silver plus because silver plus has no appreciable Bronson-Lowry acid-base behavior in water. That was sort of a mouthful, long story short, silver plus AQ, you can write that. So, first thing that I'm going to do, I'm given a KSP value. Let's write that down. No, for silver chloride solid in water at 25 C, that's just about where we're at right now. KSP equals 1.7 times 10 to the minus 10, small number. Now, since I've got no multipliers here, because my salt is just one cation, one anion, monocation, monoanion. This is going to be an easy one to write, concentration. So plus times concentration, Cl minus. Now, the way I represent these, I use a lowercase s. You guys can just write a regular s. I'll keep using the cursive thing so you're used to seeing it, because I think that's what that does. S times S. Now, if you guys have taken calculus 3, S squared. So, this is a pretty easy one to solve. Once again, 1.7 times 10 to the minus 10 equals S squared. So S, my molar solubility, is going to be root 1.7 times 10 minus 10. You can plug that into your calculator, or that's probably done the math for us. S equals 1.3 times 10 to the minus 5. All right. Now, more importantly than anything we've just done, what does that number tell us?
That silver and chloride have the same color.
Tells you about well, specifically, yeah. More generally, in this case, S tells us both the concentration of silver and chloride ion. Now, this will not always be the case, but since I've set these two variables equal to S, I know that 1.3 times 10 to the minus 5 equals concentration, 7 plus, equals concentration chloride, all AQ. So any questions on this? So again, we don't have a denominator here, so this is even easier than stuff you guys were doing before.
Would you always set products equal to S, or are there like certain situations?
You're a half-page ahead of us. All right, so we solve for a number. While that's fine and good, Dr. Horvath asked why, and can we make sure that number is reliable, in his words. Bottom of page 19.2, can we be sure that 1.3 times 10 to the minus 5 molar is a reliable estimate of S for this system? Now, that is, can we be sure that the dihydrate of silver plus and chloride show no appreciable Bronson-Lowry acid-base property? Now, chloride ion, that's the easy one. Is that going to be Bronson-Lowry active? No. Why is that? It is a weaker base than water by far. It is the conjugate base of strong acid, hydrochloric. Makes it a good, stable anion in solution. Now, what will we do here? Well, if I wanted to, I would just take a soluble silver salt, say silver nitrate. I would dump a bunch of it into water, and I'd take a pH meter or some pH paper, dunk it in, and see if it's an acid. Turns out it's not. So this is something you could solve for in lab. Is silver plus a Bronson-Lowry active cation in water? It is not. Let's see here. Oh, yeah, he does the same thing. So if we look at the top of 19.3, thus, since the pH of 0.1 molar silver nitrate is 7.0, it follows that hydrated silver ion has no Bronsted-Lowry acid-base properties. The consequence of water solution, case closed, we're good. Move on. Any questions? Yeah.
Is that since its charge is only +1?
Yeah. So for silver on the periodic table, lead and copper. So we know as you go from energy level 3 to energy level 4 in the transition metals, these get much, much larger. Silver's big. Not only is silver big, but it's only got one positive charge on it. So the positive charge density on it is small, which means it's not going to want to kick protons off of water. So, long story short, yes. Positive charge density is the reason why. For instance, we know that if we have something like aluminum below boron, or iron 3+, those are Bronsted-Lowry active metals. Those are acids, and not only are they acids, but they're polyprotic because they have much higher positive charge density. And Horvath talked about that earlier last week. Okay, yes, you know that. So that is exactly the reason why. Silver's big, and it's only got a 1+ charge on it. So neither of those are Bronsted-Lowry active, which is good for us because it simplifies our problem solving. Still have time left. Wonderful. All right. So next question. What is S for silver chloride in a solution of 0.10 molar calcium chloride? So, what do I have here? Well, first I'll write out the system that I have. 0.1 molar calcium chloride. Now, what's my concentration? Calcium chloride is a soluble salt. You don't have to look any of that up. Calcium chloride goes right in. So, what's my concentration of chloride going to be? .2 mole. From stoichiometry. Never forget that. That's an easy mistake to make, especially under exam pressure. 0.2 mole. I also know that I have a concentration of calcium ion. It's not going to be important to us, but if we want to start assembling a quantitative principal species inventory, does he say species or system now? Species. Okay, good, got it right. All right, 0. So, now, if I dump silver chloride into this mess, I know that this equilibrium is eventually going to be established. Same one that I wrote before, but it bears repeating, so I'll write it again. Now, I'm going to go ahead and I'm going to write out KSP again, and we'll see where we run into a hitch. Now, if you guys look ahead in the text, you'll know exactly why, but if you haven't, reason out why I can't just call this S and S.
Because you have more CO.
I got a bunch of chloride ion floating around in the solution. There's no way I can possibly do that. Because, according to Le Chatelier's principle, if I have additional chloride ion in this solution, my equilibrium is going to be destroyed for what I have here, and it's going to be pushed over in which direction if I add product? The left. So, what I'm doing, I can think of it the other way around. If I have a saturated solution silver chloride, I add some calcium chloride. S is going to become smaller because now I have another source of chloride ion in a very soluble salt. So, the way I'll name this, I don't have another source of silver ion, so I'll still call that S. But, for chloride ion, I know that I'm going to have a contribution from KSP, however small. I'll call that S. But I have to add to that the chloride ion already in solution, plus 0.2, we'll leave the molar out now. Now I wrote brackets there, you could write parentheses because we'll turn it into a mathematical equation. But this is what I have to solve now. Because, once again, calcium chloride, dumped chloride into the solution. Now I realize that S is going to be smaller because I've got S plus 0.2 here. Now, if I want to go ahead through and I'll solve this, one logic question. I solved for S over here. 1.3 times 10 to the negative 5 mole. What's S plus 0.2?
The same.
The same.
Yes. Is that, you said S plus 0.2 equal to 1.2 times 10 minus 5.
What did you point to?
0.2.
2.2?
Yeah. So 0.2 plus 1.3 times 10 to the minus 5, unless I had a very accurate
Oh, just point to as well.
sense of chloride ion, 0.2 is so much larger
Right.
than what my S value is going to be here, assuredly, because I know S is going to be smaller here, that I can go ahead and ignore S, which is very similar to ignoring X in M sub I minus X, when you guys are looking at acids and bases. So, what do I have now? Got KSP, 0.2 times S, which gives us an S value
2.6 times 10 to the negative 6.
Horvath gets 8.5 times 10 to the minus 10. So let's see here. Yeah, so 1.7 times 10 to the minus 10 divided by 2. Divided by 0.2. 8.5 times 10 to the minus 10. That seems about right. What was the number that you got?
Oh, I think I forgot about the 1.7 times 10.
Okay. Yeah, so 8.5 times 10 to the minus 10 seems about right. So, this is now the contribution by KSP to the system for silver plus and chloride ion. Now, if I were asked the question, what is the concentration of chloride ion and the concentration of silver ion in this system, I would say, well, I know that I've set S equal to silver plus. Okay, that's easy. Oh, whoa, whoa, no equals. So 8.5 times 10 to the minus 10 equals S. I've set that equal to my silver ion. And I know that my chloride ion is equal to S plus 0.2. We already proved to ourselves, 0.2 plus 8.5 times 10 to the minus 10. So, and concentration chloride ion, for all intents and purposes, remains 0.2 mole. That's a cathode. So, that's what happens if we have a system repeating source to provide cation, anion, or cation. Now, does anyone have any questions on how we solve that? So basically, we just have an initial molarity of one of our species, so we have to include that in our K, because our K is going to be all inclusive. Yeah?
So since the concentration of Ag plus is really low, a lot of it remains in GCO form.
Oh, absolutely, yeah. I mean, so we call these things semi-soluble because, I mean, if I just take a pinch of, something, silver chloride or whatever, and I put it in water, I'm still going to see some, even in like a liter of water. I'm still going to see a little bit there. But an equilibrium does exist, and it is measurable. 1.5 or 8.5 times 10 to the minus 10 molar is still a measurable concentration. Not in lab by like the stuff that you guys do in lab, but with more advanced instrumentation, you can detect stuff like this, and that's how we know.
So what happens to the calcium in the
Oh, calcium is still there, but calcium is a spectator in this system because the equilibrium with which I'm dealing is all silver chloride. So the first reaction that I'd write down, if I really wanted to be sort of all-inclusive here, I'd write CaCl2. No equilibrium arrows. Ca2 plus 2Cl minus. So the calcium ion is just sitting there. Now, if I wanted to, if I'm taking something, say like calcium carbonate, then I don't care about chloride. I care about calcium. If calcium carbonate is my semi-soluble salt, we'll deal with something that a little bit, or something like that a little bit later on. Okay. Any other questions herein? Okay. Time is currently 1:44. So, questions 19.1 and 19.2. You guys should be now fully equipped to solve. Go ahead and give those a try. It shouldn't take you longer than 5-7 minutes tonight for your discussion sessions tomorrow. And thank you for staying awake. We'll see you on Monday.